Hi everyone, this is lesson 3.7 for Algebra 2A, and this is on function composition or composite functions. You did do this last year in Algebra 1, so some of this might look familiar to you. We're just revisiting it this year in a new context. And function composition is not a super tricky topic. It's really just taking two functions or two processes and mashing them together. So applying the process and steps of one function to a variable, getting an outcome, and then applying another function's processes and steps to that outcome, okay? So just to give you kind of a visual, we know that functions work like a machine, right? So we can take this function f, right? And we can drop an x number into it and have it spit out an outcome like y. That's how functions work. You drop a number in, you get a number out. What composite functions do is then take another function, like let's say g, and they take this outcome and they drop this into the new function to get another outcome. And so under the composite function, we would say that this original x maps up eventually with this z. So it's just taking one function and then applying another function to the outcome, okay? So two types of notation, two ways you're going to see us write these functions. The first way is just kind of a mashup of the notation that I used here, and that would look something like this, g of f of x, okay? And so this is really just saying do f of x, get the answer from f of x, and then put that into the g function. So we really just took this and put it right in here for the g function. Now, somewhere along the way, mathematicians decided they didn't like all of those parentheses, and so somebody developed another type of notation where instead of using parentheses, they just use this little circle. And that's really saying the same thing. This is still saying take f of x and then take the outcome from f of x and plug it into g. So with either one of these notations, you're always starting with this inside one, or the one on the right, and then you're applying it to the outer one. Now, that's going to be important in relevance of this next question. Is compositions of functions commutative? Just to remind you what commutative means, commutative is like multiplication. You can do 3 times 5 and 5 times 3, and they both come out the same. The order doesn't matter. And so the question we're really asking ourselves when we ask about function composition being commutative is, does f of g of x equal the same thing as g of f of x? That's the question we want to know. So to do this, I'm going to test out both of these things. I'm going to start with, well, actually I'm going to start with this one. I'm going to plug a number into f of x, get the answer, plug it into g of x. And then I'm going to take that same number that I started with back here, plug it into g, and then plug it into f and see if it comes out the same. And I'm just going to pick a number, all right, and we'll test this out. Now, if this works and it is commutative, then I would have to do a lot more work to actually prove this. But if it doesn't work, then I've disproven it. Then I've shown that it's not commutative, okay? So I'm going to just pick 5, let's say. So I'm going to do f of 5 equals 3 times 5 minus 1. So that's 15 minus 1, which is 14. And then I'm going to take that 14 and put it in over here. So 14 squared plus 1. 14 squared is 196, plus 1 is 197. So applying it in that order, this was really what I just did was this, g of f of x, because I started with the f of x and then I plugged it into g. The 5 that I started with initially was mapped to 197. Let me do that the other way around. So I'm going to start with the g function, and I'm going to drop the 5 in there first. So g of 5 equals 5 squared plus 1, which is 26. And then I'm going to plug that 26 into f. So f of 26, that's 3 times 26 minus 1. Well, let's see, 3 times 26 I believe is going to be 78, minus 1 is 77. And because this answer did not come out matching this answer, my answer here would be no. Function composition is not commutative. So the order that you apply the functions in makes a difference. Okay, me starting with g of x or starting with f of x made it so that I got different answers each time. So you do have to pay attention to that order and always make sure you're starting with the inner function. So we are really just doing one example here because I really think that's all you need. Okay, so I've given you two functions here, f of x and g of x, and we're going to start with just some calculations, and then we're going to get into some more complex stuff where we're actually writing new functions. So with this one, remember I'm starting with g of 4. So I'm plugging that into the g function up here, so that's 1 over 4 minus 9, which is negative 1/5. And then I'm taking that negative 1/5, and really what's happening is now I'm saying I know g of 4 is equal to negative 1/5, so now I'm calculating f of negative 1/5. Well, that would just be negative 1/5 squared, which is 1 over 25. So I would say under the composition of these two functions, my original value of 4 matches up to 1 over 25. Okay, let's try with the next one. And the next one, let's see, it looks like I'm starting with the f function this time instead of the g function. So I'm going to go f of negative 5. That would be negative 5 squared, which is 25. And then I'm plugging that 25 in right here. So I'm really doing g of 25, which is 1 over 25 minus 9, which is 16, so that's 1/16. And that would be my final answer there. Sorry, that pen's really light. Okay, let's try f of 3. Now that one looks a little weird, right? Because that one's like 2 f's in a row. All this means is we're taking the f of 3. Well, let's just work through it one piece at a time. So we'll start with f of 3. F of 3 would be 3 squared, which is 9. And then this is just saying, okay, now we know this f of 3 is equal to 9, so now do f of 9. I'm just applying the f function again. And so then I would just do 9 squared equals 81. Okay, so it's applying the same function twice, but you're still composing the two functions. Okay, so now when we get into the ones where you want to write a formula, now I'm not working with a specific value of x, I'm working with the entire g of x function. So this is telling me to take this entire g of x function, pick it up, and plug it into this function. So here's what that's going to look like. If I think of this as being kind of my shell or my frame, it's going to be, here's my x squared, but in place of x, I'm putting in 1 over x minus 9. Now, when I actually go to simplify that, when I want to square that, I would square the top, so 1 squared is just 1. On the bottom, this would really become like the quantity x minus 9 squared. If I was being super technical about our simplifying, we should really FOIL that thing out. But really, in most cases in math, this is simplified enough, so you could leave it like that. However, if you had other numbers to combine with it, you would have to go ahead and FOIL that and clean it up. But that's where I'm going to leave my final answer there. So for the next one, g of f of x, this means I'm picking up the entire f of x function and plugging it into g of x. Okay, so here's my frame, 1 over something minus 9. And in place of that x, I'm just putting the f of x function, which is x squared. So just to write that a little cleaner, there's really no simplifying to do on this one, is 1 over x squared minus 9. Okay, now the fun questions. We need to talk about domain for all of these functions, okay? Because we now have 4 different functions. We have f, we have g, we have f of g, and g of f. And these two are different from each other. Okay, notice this one the square is only on the x, this one the square is on the whole thing. So remember when we're thinking domain, we want to be thinking about what is x allowed to be. I think it's probably easier to think about anything that x might not be allowed to be. So when I look at f of x is just x squared. I don't have any restrictions there. Mathematically, I can put anything in there and square it. So my domain for f of x would just be all real numbers. Okay. Let's look at g of x. So with g of x, what I need to be careful of, because I'm working in fraction land here, is I can't let the bottom of that fraction equal 0, meaning I can't put a 9 in right here. So for my domain, I would say all real numbers except 9. Excuse me, guys, sorry. So now let's look at this first composite function we did, the f of g of x. Whoops, I'm messing up my own notation here. When I look at this function here, I want to be thinking about what is x not allowed to be. Well, I'm in really the same situation I was back here. Yes, technically that's being squared, but that just means I have 2 copies of that thing. So I still can't let x be a 9, because 9 minus 9 would give me 0. 0 squared would give me a 0 on the bottom of my fraction. So I'm sticking with that same domain. All real numbers except 9. And then last one here, g of f of x. For my domain. Looking at this function, now this one's a little bit different. A 9 would actually be okay here, because 9 squared minus 9 does not give me 0. But I want to think about what x value would make that bottom equal to 0. This is what I'm thinking here, and you might not even have to write this out, but x squared minus 9 equals 0. So really I want to think about what x squared would give me 9. And that would be 3 or negative 3. So I would say my domain is all real numbers except plus or minus 3.